the point to collections. Go check out Metaplex's docs for that. And we'll say UMI and then the options for our collection. Mint will be the collection mint, which is just that key pair we made earlier. The name, let's call it, my collection. Symbol, MC. I don't normally like using symbols for connections, but Solana Explorer says no symbol if you don't have a symbol for your collection. So that's the only reason I like to do it. A URI. I'll talk about this in a second. URI, pardon me. Add that comma. What else? Seller fee basis points, which I will say is a percent amount. Of 0. Seller fee basis points are a way for artists to make money on secondary sales. So if an artist sells an artwork to somebody, then a couple of years later, particularly as that artwork has increased in value, that person transfers it to another person, then the original artist can make a royalty on each of those transactions. That's actually a really good idea. But these days, we actually have newer, better ways of handling this, because this basis points on NFTs used to just be enforced by marketplaces being nice. These days, we actually have things that are built into the protocol, like programmable NFTs and like transfer hooks that can be used to provide a mechanism for artists to get those royalties and enforce them, so people can't actually transfer that artwork without paying the original artists. Very cool, particularly for people who make money as artists for their living. And yeah, if you're interested in that, you should check out Token Extensions. There's a lot of really good things in there. Seller fee basis points and is collection, let's say true. Great. And it looks like we need to import percent amount. That's percent amount. Where do we get that? It's from, Metaplex Foundation, UMI, key pair. So just after key pair identity, let's add percent amount. There we go. And that all looks good. So after we've made our transaction, we can do await transaction dot send and confirm, and we'll use our UMI instance to connect out to Metaplex's tools on the Solana DevNet, and that looks good. So we've loaded our user, given them some Sol, connected to DevNet, created our UMI instances, and created our NFT to represent the collection. We're going to actually fetch the NFT that we've just made. So const created collection NFT equals await fetch digital asset UMI, and then we say collection mint dot public key. Yeah, fetch the NFT for the collection at that address, and then we are done. So console.log. Sometimes it feels like VS Code is heckling me when I type, and I will say, what will I say? Created collection. I will pick a nice emoji for a box because the box has the collection in it, and I like logging emojis. The address is, and then let's use Get Explorer link. And what do we want? We want a link for the address of our created collection NFT dot mint dot public key, and we want a link for DevNet, please. So that looks good. Let's just run through our script to go through it again. We have our connection to DevNet. We're loading our user from id.json. We're giving them some DevNet Sol if we need to. We're creating an instance of Yumi, which we'll use to talk to various tools. And we're saying the specific tools we want to talk to are the MPL token metadata program. In other words, Metaplex. We're creating a Yumi version of our user and saying that Yumi should use that to sign all our transactions. Just making a key pair, then creating an NFT, which is going to make a mint using that address. And that NFT is a collection NFT. So you'll see, is collection true? That is our collection NFT. We're going to send that transaction and then refetch it from that address. We can run this, but first we need to talk about this URI. So that URI should be a JSON file that you've uploaded somewhere and that you can access directly via that URI. For this case, I've just used GitHub's raw URLs. So that's when you upload a file to GitHub, you can click on it and see the raw URL. What you want for that URI or URL, they basically mean the same thing, is that when you load that in your browser, you just see the JSON file. You shouldn't see any HTML or anything else around it. So if you look at my screen right now, it's just straight up JSON. All it has is a name, a description, and an image. Also with that image file, let me show you the same thing. When I load that image, the image just loads itself. No surrounding HTML, no anything else. You'll need both the JSON file and the image file mentioned inside the JSON file to be able to load up directly without anything else around it. Again, in GitHub, you can just use a raw URL, which is fine for our purposes. There's quite a few of these permanent online file storage services. You can pick the one that works for you, but the thing that makes them permanent is they're, like Solana, decentralized. So they can store your JSON file or your image online for a really long time. They're not reliant on any individual cloud provider. So when people buy your NFTs in production, they can know that the JSON and the image will be around online forever. So we've got our image and we've got our JSON file. And when we load either of those URLs, we just see the image or the JSON file. Let's take the address we've uploaded our JSON file to and paste it into our URI field for our collection. So that looks good. We probably also want to install ESRun because we're about to run it. So npm I ESRun. ESRun, if you haven't seen it before, is just a really easy way to run TypeScript on the command line. You don't have to set anything up beforehand, it just works. So now that we've installed ESRun, we can just run our TS file. That's npx ESRun create collection.ts. So we've loaded our user, we've set up an Yumi instance for that user, and you can tell it's thinking. It's going to go make our collection for us. Beautiful. So it's made our collection, and because we did that Git Explorer link, it's even given us a beautiful link to click on. So we can see in Solana Explorer, make that a little bit bigger for you, that our collection has loaded. The symbol is MC. The master edition is a way of saying that this is a collection. And you can see a bunch of different information about this. There's only one of the collection. There'll only ever be one. And it has a bunch of other fields that are common to regular tokens. Things like a mint authority, like who's allowed to make these, a freeze authority, who's allowed to stop them being moved around, and an update authority, who's allowed to change this, which are all just public keys. The update authority you'll see is the public key that matches our id.json file. And if you scroll down, you can see when this NFT was created in the history, you'll see 2 minutes ago that that transaction ran. So that was our transaction running through Yumi. Great. So we have our collection. Let's make an NFT that's a member of our collection. And then let's also verify as the collection owner that that NFT belongs to that collection. We're going to make another script here. And what should we call it? We'll call it just create nft.ts. And I'll save that. I'm going to just copy all the imports and probably the user and the airdrop and the Yumi user, because we can reuse all of those. We might not use all the imports, but we can just delete the ones that we don't use. So in create NFT, we've pasted in everything from our previous script all the way up into we set up the Yumi instance. the next thing we'll want to do is save the address for our collection, because we're about to use it to make the NFT that belongs to that collection. So let's do const collection address equals, we'll say new public key, public key. And we will get the address from our collection. I'm just going to use our Explorer. We could also get it from the command line. New public key, and that address. It's complaining about public key. It's just because it's unused, but that's okay. And we'll need to import public key from Solana Web3.js. We could also, if we wanted to, do it this way as well. Because Umi has its own format for public keys, we can also just go public key, which is actually a function that comes with Umi, and there we go. That also works. If we do the normal Web3.js method of doing new public key, then later on we'll have to convert it to the Umi public key anyway. So we may as well, which is actually done with the same function. So we may as well just use the function in the first place and just go collection address equals public key, the function, and then the address of our collection that we got from Solana Explorer. So we've got our public key. Let's go make our NFT. Console.log creating NFT ... Oh, sorry. VS Code gave me a great suggestion, which I also don't care about. Creating NFT ... The NFT has its own mint, as again, I mentioned each NFT has a unique mint address because they're unique. Generate Solana Umi. That's going to be just a new key pair that we make. And then let's actually make the transaction to create an NFT. So const transaction equals await create NFT. We'll say our Umi instance, and here's the options for our NFT. The mint will be the mint address we just made. The name of our NFT will be my NFT. The URI will be another off-chain data file. I'll just put ... in there for now. Seller fee basis points, same as earlier. We'll just say %amount 0. And we'll add some information about our collection. We'll say the key of our collection, the public key of our collection, is collection address. If we, actually, I'll tell you about that in a second, and we'll say verified false, just because when we first make this NFT, verified will be set to false. In a second, we're actually going to sign or verify that NFT being part of our collection. And that will change verified to be true for us. Then we'll do await transaction, send and confirm using our Umi instance. So we've made a transaction to create our NFT. We've said that it's a member of the collection that we made a moment ago, and we've sent that transaction off to Umi to be processed and make everything for us on the blockchain. Let's go fetch the NFT we just made. So const created NFT equals await fetch digital asset, and using our Umi instance, we're going to fetch the asset that it's at, the NFT's unique mint address, mint.public key. And then let's make a pretty console log. So console log, and I'm going to add a little artwork emoji because that's cool, and we'll say created NFT, address is, and then we'll do get Explorer link for address using created nft.mint.public key, and we want a link for devnet, please. That looks good. So that's our whole file. I'll just go and remove any of these imports that we're not using. We ended up not using public key from Web3.js. We ended up just using the public key from Metaplex Foundation UMI. It's a little bit weird, UMI having different formats for public keys from Web3.js, but hopefully that will be fixed in future. I think everybody's moving to the new web crypto style of public keys, so that will get better in future. So finally, before we run this script, I wanted to talk to you about that URI. So just as we saw with the collection, that URI needs to be a file, a JSON file stored online, and that when you open it in your browser, you just see the contents. So I'll open up another tab here and show you. For an NFT, it's just a name, a description. You can add a symbol if you want to. I don't feel like adding a symbol for this one. And an image. The image inside also needs to just load directly when you load it up in your browser. So it's this cool ball with energy bits. That looks nice. Same as before, if you're making NFTs that you are selling in production, use one of these like permanent online file storage services. That means that your JSON file and your image will be online forever. So I will paste in my uploaded, not the image file. I want the JSON file. There we go. And I will run our script. So just clear my screen, npx es run, and then create nft.ts. Let's make our NFT. So it's loaded our user, set up our UMI instance, and it's making our NFT for us. Give it a moment. Great, we've made our NFT. So if we click on that URL, I use a Mac, so it's command click to open up a URL. We can now see our NFT. It has the artwork, that is the artwork that we uploaded before. This actually, NFTs can have a bunch of different files. This just happens to be an image, but we could also use an MP4 video. We could use a 3D object like an FBX file or an OBJ. The name of our NFT is the name from the JSON file. We didn't set up a symbol, so it says no symbol was found. And yeah, it's a bunch of other normal token options, like there's a maximum of one of them, and there's only one of them supplied because NFTs, if you look at them as being regular tokens, are unique. Seller fee basis points is 0%, as we said earlier. And you can see that it was created a couple of minutes ago, 2 minutes ago, in fact. We didn't set up any attributes on our NFT, and if you look in metadata, you can see a bunch of things like where the JSON file is, which is where it got that image from. And you can see the creator. The creator is 0. The first creator is our address from id.json. And you can see the collection, which is the collection that ch file, that ch public key that matches our collection that we made a moment ago. You'll see that verified is 0. Let's verify that NFT as being part of that collection so that it turns that verified to 1. Also, art tools, particularly wallets or galleries or art marketplaces, really like it if you have verified set to 1. There used to be that people would run around and make an NFT that was a fake NFT that looked like it was a member of a real collection. So having verified NFTs is a way for the collection owner to say, yes, this NFT is a part of my collection. So let's do that now. We're going to make a new file, and we'll call it verifynft.ts. And because I don't like typing, I'm going to steal everything from that first file again. So just loading up our user, giving them some Solana, setting up our UMI instance, and all the way to set up UMI instance for user. So I'll just paste that in. And to verify an NFT, it's actually pretty simple. It's only yet another, just a single transaction. So we've made our create NFT script and we've pasted in everything all the way up to setting up our UMI instance. We'll need to set up our collection address. I will steal that from our create NFT script. And we also need to set up our NFT address, NFT. And what was our NFT address? I'll get it from Solana Explorer. 84 something or other. That sounds good. And it looks like we need to import that public key, that function, which is part of UMI. There we go. Cool. So we have just a pretty default UMI script with a collection address and NFT address set up for us. So we've pasted in our collection address and our NFT address into verifynft.ts. The only thing left to do is actually make that transaction that verifies that this NFT is a member of this collection, and that will flip that is verified to true on the NFT. So let's make that transaction. Const transaction equals await, and it's called verify collection v1, and it takes an UMI instance and a bunch of options. The options are the metadata, and this is the metadata for the NFT that we want to verify. We'll actually use a little helper. It's called find meta PDA. It comes with Metaplex. And we'll just give it the options. Find the metadata PDA for this mint, which is our NFT address. NFT address. Beautiful. The collection mint, which is our collection address. Nice. And an authority, which we'll actually just say is the user running UMI. So if we do UMI.identity, that is our authority. We could also say authority is UMI user. Same thing. It just means one says it's this particular key pair. The other, it says it's whoever is running UMI, which is also the same user account, the one from our id.json. So we do transaction dot send and confirm UMI. Beautiful. And then we'll do console.log. And let's use some cool emojis. I will use a big old tick for being verified. And we'll say NFT verified. And let's give it the NFT's address. NFT as member of collection, and we can say collection address, and let's also say see explorer at, and we'll say get explorer link for an address, which is the NFT address on DevNet. That looks good. Excellent. I'll just save it and format it. And everything looks good. I can remove some of those unused imports. Don't have to, but I just want to keep our file nice and ensure there's no dead code. Let's go and run our verify nft.ts. I'll clear my screen and do npx esrun verify nft.ts. Give it a moment to run. And it looks like it's finished already. That was really quick. Let's go check our NFT. And what we're looking for here is in the metadata. There we go. Verified is now set to 1. Explorer actually updated while I was looking at there. I was worried for a second. Yeah, cool. Great. So our NFT is now verified as a member of that collection. So now we have a beautiful NFT. If we click creators, our wallet address is shown as being the creator. That NFT is verified as being a member of a collection, which means that wallets and galleries and art auction sites will show our NFT nicely because it's important that NFTs are verified as being parts of collections. We have a beautiful collection. And yeah, we can transfer this NFT to people. We can set it up on auction sites. We can make dApps that use this NFT to like token gate access to something. That can be a real world experience or a digital experience. If you want to learn more about Metaplex's tools that we were using in this lesson, the tool we were using is called MPL Token Metadata. So if you Google that, you'll find all the documentation about that tool. And if you want to learn more about Solana, I will see you in the next lesson.
Our next smart contract allows users to offer an amount of one token to exchange for a desired amount of another token. For example, Alice wants 100 dog tokens and is offering to swap 10 USDC. Without our program, the users would have to swap with each other manually. But what if Bob promised to send Alice 100 dog tokens but took the 10 USDC and ran? Or what if Alice was dishonest, received the 10 USDC and decided not to send the 100 dog tokens? In the traditional finance world, when Alice swapped with Bob, there would usually be someone in the middle holding the funds temporarily and taking a percentage of the transfer for themselves. But in blockchain, this is solved with a swap program, also called an escrow. Our program will transfer the funds provided by Alice into a vault account and store details of her offer, like the amount and type of token she wants, in another PDA. When Bob decides to take the offer, our program will transfer Bob's tokens to Alice and transfer the funds in the vault to Bob. Now remember, in traditional finance, someone would sit in the middle, taking a couple of percentage points of what Alice and Bob are offering. But with our smart contract, Alice got 100% of the tokens Bob sent. Bob got 100% of the tokens Alice sent, and they got what they wanted without having to trust each other. Fees were only a fraction of a cent. That's the benefit of decentralized finance. Let's get started.
So let's make a swap program. First thing I'm going to do is run anchor init swap, and I'm going to use the multiple files template. Because this project is a little bit larger than, say, our favorites program, multiple files will split our program up across different files and directories just to organize our project a little bit better. So -- template equals multiple. Give it a moment to install. Great. I change into that directory, and let's open up our editor and have a look around our new project. So here's our project. The actual anchor program is in the programs swap directory, and the TypeScript tests are in the test directory. Programs swap is also a little bit more interesting than the normal single file layout. There's still a librs, but helpers that are specific to each instruction handler live in the instructions directory. There's a state directory for storing basically the structs for the accounts you're going to make. A constants file, I should say. And yeah, it's just this will make things a little bit neater for us. So the first thing I'm going to do is add some dependencies, because we're not just using Anchor here, we're also using Anchor SPL, which helps us do things like transfer tokens around. So let's do that. Let's pop open cargo.toml, and just where it has the anchor lang, we're going to change that to look kind of like a little object. We'll say version equals 0.30.1, and we'll also turn on the features equals init if needed. Init if needed allows us to create an account, add an address if it doesn't already exist. We'll also add our Anchor SPL. And what version? The same as our version of Anchor, so 0.30.1. And we may as well just say the current version of Solana program as well. It was 2.0.3. Great. So we now have our program with Anchor and Anchor SPL installed and the init if needed feature turned on. I'll just fix that typo. Great. Something else is we should probably also look at setting up our constants. I'm a big fan of avoiding magic numbers when I program. So if someone else is reading my code, I don't want them to see 8 plus 32 plus 32. I just want them to see variables that make sense to them. So in Anchor, I'm often adding 8 things to get the true size of an account on chain. That 8 bytes is the anchor discriminator. So I'm just going to do pub const anchor underscore discriminator, and that will be a, what is it? A U size. So just whatever the size is for the platform. And it's 8 bytes. It just saves us having to reference that anywhere else as well. Oh, and I'm missing an equals sign there. There we go. Great. We're also going to be transferring some tokens in this project. So let's create a helper function that just does that for us. That way we don't have to cut and paste everywhere. Instructions, new file, and we'll call it shared.rs. And in this file, we will create our transfer tokens function. So that's just going to be pub function transfer tokens. And we're going to take this generic, which is the Rust lifetime specifier. This is telling Rust how to hold onto a bunch of the variables inside this function. And what we're saying with this lifetime of info here is just hold on to them for as long as you need to hold on to the underlying Solana account info object. If you don't know what that means, that's fine. This is not a Rust, and it's not a Rust course. This is a Solana course, but you can read up about Rust lifetimes in the Rust book. Cool. So we're going to say from, and that's going to be a token account. Token account is fine if we wanted to make our project specific to either the old token program or the new token extensions program. But if I wanted to make my program work on both of those, then there's a thing called interface account, which is just a way to have our program work across tokens that are made with the older token program or the new token program. That will last for as long as info does. And you can see here how we wrap around our token account. We're also going to borrow that value as well. We should add a return type for this function. So it's just going to return a result of nothing. That looks nice. We should probably also, for our share.rs, we should actually expose it from our module, because I can see that everything is a little bit dark and gray here. Let's do that too. So we've got pub mod initialize and pub use initialize. Let's change that to pub mod shared and pub use shared star to expose everything inside shared.rs. And you can see that the gray has gone away now. You can also see that interface account is red if, Anchorlang prelude interface account. That looks good. Yeah, I think we want that. In fact, we can just import all of the anchor prelude, because it's kind of a bit of a normal anchor thing just to import the entire prelude. That gives us all the what people often call the goodies from Anchor without having to type the full path to any of them. We'll probably also need to import a bunch of things from Anchor SPL. So let me do that, like token account. And we want to import it from Anchor SPL token interface, because that is the magic that allows our program to work on both the older token program and the newer token extension program. That is looking a little bit better. I'll just fix a little typo there. And I will also turn on word wrapping so you can see what I am doing. There we go. Cool. So there's still a little bit of red there, but it's just saying that we're not returning a result yet, which is true. We're not returning a result. I'll also neaten this up a little bit. There we go. And let's add more of these options for our transfer tokens function. So we have a from, which is an interface account. We'll also have a to, which is an interface account, also wrapping around token account. An amount, which we will also borrow, and that will just be a U64. A mint, which will be a pub key. Same thing, we'll do interface account. Oops. And we will, it's going to live for the lifetime of the account info object, and it will be a mint is the anchor type we're using there. We'll have an authority, which will be signing this transaction. So borrow signer, and that has a lifetime of info. We'll also have the token program be one of our options as well. And the way we say that, to say that our token program can be the older token program or the newer token extensions, is interface. And that lasts for info. And then we say token interface. There we go. That looks good. So the way we actually transfer tokens is we call the token program's transfer checked function. Transfer checked just does a little bit of logic, making sure the mints are okay, and a bunch of other useful safety features. This is the reason we use Anchor, because it provides us with this good stuff right out of the box. So the first thing we're going to need to do is specify all the options we want for transfer checked. We'll just get them from the options we had for our argument. So we'll say transfer accounts options, and that's a type called transfer checked, a struct called transfer checked. So in Rust, sometimes you have structs, which would be interfaces if you're familiar with, say, TypeScript, that have names that kind of seem like functions. All that means is that that struct is an object that is used as an argument for that function. So we're about to call a function called transfer checked. The options for that function are called transfer checked in title case. Just a bit of a kind of cultural thing in Rust. I would probably call this, if I was writing this in TypeScript, I would call this something like transfer checked options. But in Rust, it's just transfer checked in title case. That's the options for the transfer checked function. Because we're calling just a program in raw Solana, we're not doing any anchor magic here. We're going to turn everything into the low-level Solana account info object. So you'll see transfer checked from will be the same as from and just to account info. And mint will also be mint to account info. You might be surprised to find out that to is to account info. And our authority is also the authority dot to account info. We do this once because we don't want to have to run dot to account info a bunch of times throughout our program. So that is our options. So we should just call it transfer. Yeah, that looks good. We can call it transfer accounts options. That's fine. So our CPI context. A CPI context is just really the program you're using plus the options. That's a CPI context new, and we have our token program. And guess what? It's to account info and our transfer accounts options. And that looks good. We've got a little bit of red here. I think it just wants us to import mint, and we want to import mint from the token interface option. It's that one there. Likewise, transfer checked. We want to import that also from the token interface as well. So, SPL, token 22. Just see if that looks right, because it that should just be transfer checked. There we go. We don't need any special magic there. Anchor SPL, token interface, mint, token account, token interface, transfer checked. So there are similar imports in other places. We want to make sure we're always importing the ones from token interface. So we have our CPI context, which is our program that we're about to call plus all the arguments. Let's actually call our program. So we do transfer checked and the CPI context, the amount, and the decimals, which we'll get from the mint. And that looks pretty good. We just need to import transfer checked. And again, we want to import it from probably from token interface, I think. So we'll just do it manually. Transfer underscore checked. And that looks good. No red. Everything is importing from either Anchor-Lang itself, just for the prelude, and everything else is imported from Anchor SPL token interface. Great. So we now have this reusable function wherever we need to transfer tokens, and we're going to call it a whole bunch. So that is useful. Let's also think about what we're going to write to the blockchain. As we talked about before, there's really two parts to this. There's a make offer instruction handler, which will send tokens into a vault and write information about what the person wants in exchange for those tokens. And there's a takeoff instruction handler, which will allow somebody to take the tokens from the vault and also send their tokens directly to the person that made the offer. So in state.rs, we're going to make a little file that talks about what that offer should look like. And we're going to call it offer.rs. And we're going to import our Anchor prelude again. Oops. Use Anchor-Lang, ding ding, prelude, ding ding. Star ding ding is just a personal thing I use to refer to the double colons. And then we're going to talk about what that actual offer looks like. So that's going to be a struct, pub struct offer. This is going to be an Anchor account, obviously. So we add our hash account macro. Also, we want to easily be able to work out the size of what an offer is, because we're going to have to write one of these out to the chain at some point. So there's actually a useful thing in Anchor that's called init space, which is the size taken to initialize or create this account on chain. So if you add derive init space, our offer struct, or any instances of our offer struct, now have an init space property that is added to them, or an init space trait that is added to them in Rust terminology. As we said before, this is the offer where we save details about who's making the offer and the tokens they want, etc. So it's going to have an ID, which we'll just use a numeric ID. U64 is fine. A maker, which is who made the offer, and that will just be a pub key. The mints of what they are providing and what they want. So we'll call that token mint A, and that is a pub key. And I will copy that line down, shift option down. Token mint B is also a pub key. We have token B wanted amount, which is how much they want in exchange for what they've put into the vault, which is a U64. And also, because this is a PA, we want a bump, which would just be 8 bytes. Add that missing pub, and everything is gray because I haven't actually exported the contents of offer.rs. So back in state mod.rs, I will add pub mod offer, and I will say pub use offer, everything inside. And you can see now that offer.rs looks a little bit better. What is that? Oh, I've got a semicolon on the end there. I don't need that. There we go. Nice. All the red has gone away. We are ready to move on. So we've just made our offer, which is what we're going to write to the chain. And we should probably get started on our instruction handlers. So let's open up librs and just have a look at how it looks. It is essentially the same as most other Anchor programs. There's a bunch of imports. We say our program's ID or program address. And then we have this module that we turn into an Anchor program with the program macro that defines all our instruction handlers. There's one instruction handler called initialize. Let's turn that into our make offer instruction. So I'm going to call it make_offer. I'm going to change the spelling of CTX to just be context. That way I don't have to think about it being spelt slightly different. And it's going to be a context of make offer. We'll call our accounts for make offer rather than calling them initialize. Again, I don't particularly like calling structs things that like verbs like make offer, but it's a bit of a Rust convention to if a program or a function has some options, then those options are named after the function just in title case. So inside our make offer instruction handler, I'm going to call two helper functions. The first will be instructions make offer, and we'll call that first function send offered tokens to vault. And we add a little question mark on the end to say, if this fails, throw an error, and that's okay. We expect that maybe it will fail in some cases. And our second function will be called instructions make offer save offer. Examples of failures in sending the offer tokens to the vault was, say, we tried to someone was trying to reinitialize an old vault account. We would throw an error in that function. So that question mark is just a way of saying, hey, if it throws an error, that can happen. We expect that. It's a short way of doing error handling. So we have send offered tokens to vault and save offer. That looks good. We should probably make offer. That sounds good. I think it's it's looking for make offer and it's not finding it, so it's not happy with that. So we need to make the make offer struct, which is all the accounts that will need people to specify that they're going to use when they want to use the make offer instruction handler. And we also need to make the actual make offer file. So in instructions, let's rename our initialize. And let's just call it make_offer. There we go. And happy to do any edits for us. VS Code is just updating mod.rs to specify that file is now called makeoffer rather than being called initialize. Back in makeoffer.rs, what used to be called initialize.rs, we're going to rename that to makeoffer. That struct up the top. And we will also rename handler. We'll turn that into our send offered tokens to vault instruction. And we'll work on that in a moment. Let's just start with make offer. What kind of accounts will people need when they're calling this? Firstly, we'll need their own account because they're going to sign the transaction. So we'll call that the maker. So that's pub maker. And that is a signer. Similar to before, we're going to use this info generic, which is the Rust lifetime of an account info object, to tell Rust that the lifetime of these variables in memory will be the same as the underlying account info object. So we have a signer of info. And because this the maker will pay for the transaction, their account needs to be mutable. So let's do account mute for mutable. We will need to have the mint of the token that they're putting into the vault. So we'll call that pub token mint A. We're going to use an interface account again, just to say this could be an old a mint account from token program or a mint account from token extensions. So interface account, and the lifetime is the lifetime of the underlying account info object, and mint is the object we're going to effectively wrap around. We'll also make sure that the token program used to mint that is what we expect. So we'll say mint ding ding token program equals token underscore program. We've done our import, and now we're going to have the other mint, which is token mint B. I'm just going to copy and paste that one, and it's going to have that same check that mint token program equals token program. So that's the type of token that we want, token mint B. We'll also specify where the tokens that we are about to put in the vault come from, which is maker underscore token underscore account A. That will be an interface account again, so wrapping around token account and lasting for the lifetime of an account info object, the underlying Rust account info from the Solana crate, rather than Anchor has nice names like token account, mint account, etc. Whereas the Solana program crate just calls everything an account info object. We're going to add a few anchor checks to maker token account A. The first is that it's going to be mutable, because we're going to move files out. Well, not files. We're going to move tokens out of that token account into the vault. We'll have a few checks as well. Associated token mint must be token mint A, and the associated token authority, fix that typo, equals the maker. In other words, this account actually needs to belong to maker, the person signing the program. And associated token program should be equal to token program. That looks good. I'm going to keep going because I've got a little bit of red there, but I need to finish some more things off before I look at it. Pub offer. So this is the offer account which we will be making. That's just an account. So we call it a system account, so nothing particularly special. But we will add some anchor checks, because this is this PDA where we're going to save details about what we want in exchange for our tokens. So we'll say init, i.e. make it, who will pay to create it, which is the maker, i.e. the person who signed this transaction, how much space we're going to allocate, which is 8 bytes, anchor discriminator, that's what we made in our constants rs before, plus the size of offer init space. So the size for everything to store an offer struct. Seeds will be the bytes of the word offer, the key of maker, the pub key of maker, and as a reference, the ID of the offer, and we need that to be bytes, so let's turn it into little endian bytes, and then also as ref. That looks good. Oh, and finally, because this is a PDA and we want to be efficient, we will save the bump. That looks good. Got a few things we probably need to import. Let's go and check. So we've got our anchor, lang, prelude, star, and we're importing a few things. Oh, wait a sec. We're importing a few things from our anchor SPL token interface, but we probably should be importing a few more. So I would say actually we want from anchor SPL, firstly, yes, we're happy with token interface mint, but we probably also want to import associated token. Thank you very much. And rather than just mint, we'll also want token account and token interface. That should be good. Let's add a semicolon there. And then there we go. A couple of those we're not using yet, but that's okay. So we've added those imports, and you can see there's a lot less red there. And again, always using token interface rather than some of the other imports, just so we can have that compatibility with both the older token program and the newer token extensions program. So we have our offer. We need to also use the vault account because when we make an offer, we're gonna say details of the offer, and we're gonna put our tokens in a vault account. So let's do pub vault. And that's also going to be an interface account with a lifetime of info. And that will be a token account because it's just going to store some tokens for us. Let's add some anchor goodies as well, some little checks on that account. Firstly, we're going to need to create it. So init. We don't say init if needed because we don't want anyone to be able to reuse old vaults. We'll say who is going to create the account, which is the maker. And we're going to mention a few checks that we're going to do with this. And I'll copy it from maker token account A. We're going to make sure that this token account's mint is token mint A. The authority will not be the maker. It will actually be the offer. So this token account isn't owned by a user. It's being owned by our program. Specifically, actually, its authority, rather than its program owner, is the actual offer account. So the vault account is owned by the offer account. The vault's authority will not be maker. The vault's authority will actually be the offer, because the offer PDA is going to each individual vault will be. Its authority will be the offer account. The offer account will sign for things to move things in and out of the vault. So you'll see that later on when we start transferring tokens around. And we'll also check the token program is the token program we expect. Finally, we're just going to specify the accounts of the programs we use. So like the system program, system_program. There's a program account. We'll use it for the lifetime of info and system. And likewise, we'll also use the token program. That will be another interface account because we're going to wrap around either the older or the newer, older token program or the newer token extensions program. So that's token program is a interface. Sorry, it's not an interface account, it's just an interface over info and token interface. We can actually make our project a little bit smaller by excluding this stuff, but it is best practice, so that's why we've included it in this tutorial. Finally, we have the associated token program, which is the program that maps associated token accounts to their owners and to token mints. So associated token program is a program for the lifetime of info and associated token. There we go.
So that looks pretty good. It's saying it doesn't like ID, so let's go fix that. We need to actually say in this struct that we want access to the ID that the client provided when they were making their instruction. So we will scroll up and we will say we want access to, what was it, instruction. We want the ID parameter, which is a